black hole is the only place in the universe where falling does not just mean moving downward. It means moving toward a region where space itself folds so deeply that every road, every beam of light, and eventually every future points one way. And if you actually fell into one, the answer is stranger than almost any science fiction version. From far away, you might seem to freeze. But for you, the fall would continue. The sky would distort, time would misbehave, and somewhere ahead, physics itself would stop giving comfortable answers. This matters because black holes are not just cosmic monsters sitting at the edge of imagination. They are real objects made by nature, shaping galaxies, bending light, and pushing our best theories of reality to their breaking point. By the end of this, and diseases, you will understand what would really happen as you approach one, cross the point of no return, and head toward whatever waits inside. And in the process, black holes will stop being a vague symbol of danger and become something much more astonishing. And if you genuinely enjoy space stories like this, where the science stays grounded, but the universe still feels wild, make sure to like the video and subscribe. It really helps the channel, and it lets me know you want more deep dives like this. Also, leave a comment saying where you are watching from, and tell me this. If you could safely witness just one cosmic event in person, would it be a black hole, a supernova, or something else entirely? Now, let us drift toward the darkest boundary in the known universe. Imagine a spacecraft far from home, engines quiet, instruments glowing, and ahead of you is a patch of darkness that is not empty at all. It is a black hole suspended in space, like a place where reality has been carved open. What would you actually see as you fell? Would you be torn apart before you ever reached the edge? Would time slow down, stop, or split into two different stories, depending on who was watching? And once you crossed the event horizon, would anything recognizable still happen? Or would the very idea of what happens next begin to change? To understand the fall, we have to begin with the basic truth that makes black holes so strange. A black hole is not a hole in the ordinary sense. It is not a tunnel you could simply peer into like a cave in space. It is a region where matter has been compressed so intensely that gravity becomes overwhelming. The pull is not caused by some magical sucking force. It is caused by mass-bending space-time, the four-dimensional fabric that combines space and time into one structure. Every planet, star, and galaxy does this. Black holes just do it so extremely that our normal intuitions fail. If you have heard the common image of space as a rubber sheet warped by a heavy ball, that is a useful starting point, but it is limited. It helps us picture mass curving space, yet it leaves out time, and time is not a side detail here. Near a black hole, both space and time are profoundly distorted. That is why falling in is not merely a matter of going somewhere. It is a matter of entering a region where the geometry of reality changes the rules of motion, of light, and of cause and effect. Most black holes form when very massive stars die. A giant star spends millions of years balancing two forces. Gravity pulls inward. Pressure from nuclear fusion pushes outward. For most of the star's life, these forces are in rough balance. But eventually the fuel runs low. Fusion weakens. Gravity wins. The core collapses. In some cases, the outer layers explode in a supernova, while the inner core becomes so dense that no known force can stop the collapse. If enough mass is packed into a small enough region, a black hole forms. There are also supermassive black holes, millions or billions of times the mass of the Sun, sitting in the centers of galaxies. We know they are there, not because we have seen some dark circular object directly in the ordinary sense, but because we have watched stars whip around invisible points at incredible speeds, because we have detected high-energy radiation from matter heating up as it spirals inward, because we have imaged the glowing material around black holes, and because we have listened to the ripples in space-time, gravitational waves, when black holes collide. Black holes were once a theoretical consequence of Einstein's equations. Now they are part of observed astronomy. But saying a black hole exists is still not the same as saying what it is like to fall into one. And that is where things become more intimate, more unsettling, and more fascinating. First, let us clear away one popular misconception. Black holes do not roam through space, vacuuming up everything around them like cosmic whirlpools. If the Sun were somehow replaced by a black hole of equal mass, which is not something nature is likely to do politely for demonstration purposes, Earth would not suddenly get sucked in. Our orbit would remain almost exactly the same. Gravity depends on mass and distance. A black hole with the Sun's mass would pull on Earth just as strongly as the Sun does now. The difference would be that it would emit almost no light, and the solar system would become a catastrophically cold and miserable place. What makes black holes dangerous is not that they are magical vacuum cleaners. It is that if you get close enough, their gravity becomes extreme, and there is a boundary around them called the event horizon. This is the crucial line. It is often described as the point of no return, and that is accurate, but it is still easy to misunderstand. The event horizon is not a physical surface like the skin of a balloon or the crust of a planet. You would not smack into it, or you would not feel a sudden jolt when crossing it, at least not necessarily. If the black hole is large enough, and the local tidal forces at the horizon are modest, you could pass through without any immediate dramatic sensation at all. That is one of the first deep surprises. The most important boundary in the black hole is invisible. Why can nothing return once it crosses? The simple explanation is that inside the event horizon, the escape speed exceeds the speed of light. Since nothing with mass can be accelerated past the speed of light, and even light itself cannot climb out, everything is trapped. But there is a deeper way to think about it. Outside the horizon, moving inward is a choice. Inside the horizon, moving inward is as unavoidable as moving into tomorrow. The singularity, if our current equations can be trusted that far, and lies not merely somewhere ahead in space. In a disturbing sense, it lies ahead in your future. That wording sounds poetic, but it is rooted in general relativity. Near a black hole, space-time is curved so strongly that the paths available to any object all tilt inward once the event horizon is crossed. Outside, you can move left, right, inward, outward. Inside, outward stops being a usable direction in the normal sense. It is like trying to avoid the future by walking north. That is not how the geometry works anymore. Now, picture the approach. You are still far away. The black hole may not look like much at first, especially if it is isolated and not actively feeding on surrounding gas. Black holes do not shine on their own. You see them by their effects. If there is matter spiraling in, that matter can become extraordinarily bright before crossing the horizon. Gas in an accretion disk rubs together, compresses, heats up to millions of degrees, and blazes in X-rays and visible light. In that case, the black hole is outlined by violence, a bright whirl of superheated plasma around a dark center. If there is little matter nearby, the black hole itself appears more subtle and more unnerving. It is darkness, yes, but a very specific kind of darkness. It does not merely block the background, it distorts it. Light from stars behind the black hole is bent by its gravity, a process called gravitational lensing. The star field around it appears warped into arcs and rings. Some light that would have missed your eyes entirely gets bent toward you. Some light loops around the black hole once or more before escaping. The sky can seem to wrap around the darkness, as if the universe is being pulled into a circular hallucination. This is one of the great visual truths of black holes. They do not simply hide things, they rearrange what can be seen. As you move closer, the distortion grows stronger. Stars that should be off to the side can appear shifted. Light from behind you can be bent around the black hole and reach your eyes from directions that make no everyday sense. If you were orbiting close enough, you might even see multiple images of the same star, caused by light taking different curved paths through space-time. It would be beautiful and deeply disorienting, like looking through a lens made from gravity itself. There is also a special region outside the event horizon called the photon sphere. This is the distance where light can, in principle, unorbit the black hole in unstable circular paths. For a non-rotating black hole, this lies 1.5 times the radius of the event horizon. The photon sphere is not where the black hole begins, and it is not a safe, clean ring in the everyday sense, but it matters because it marks a zone where gravity has become strong enough to make light itself curve into loops. If you somehow hovered there, the visual experience would be almost impossible by normal standards. Looking in one direction, you could potentially see the back of your own head, assuming you had made the truly questionable life decision to remove your helmet for the experiment. But before crossing any dramatic threshold, another effect begins to matter: time dilation. According to general relativity, gravity affects the passage of time. The stronger the gravitational field you are in, the more slowly your time passes relative to someone farther away from the mass causing that gravity. This is not science fiction and not just a black hole effect. It happens on Earth. Clocks on satellites run at slightly different rates than clocks on the ground, and engineers have to account for this in systems like GPS. Near a black hole, the effect becomes enormous. If a friend stayed far away, watching your fall through powerful telescopes, that friend would see your clock running slower and slower as you approached the event horizon. Signals from you would arrive increasingly red-shifted, stretched to lower energies and longer wavelengths by the black hole's gravity. Your image would dim. Your movements would seem to slow. To the distant observer, you would appear to approach the horizon ever more sluggishly, never quite crossing it. You would fade, redden, and effectively freeze at the edge. But that is not what you would experience. For you, your own clock feels normal. Your heartbeat feels normal. Your thoughts occur at their usual pace. If the black hole is large enough that tidal forces are gentle at the horizon, you could cross the event horizon in finite time and notice no sudden stop. There is no cosmic traffic cop at the boundary, announcing that you have now entered forbidden territory. The dramatic freezing happens in the distant observer's description, not in your immediate experience. This is where black holes first teach us to distrust the idea that there is one single obvious account of what is happening. Both descriptions are valid in their own frames. From far away, all you asymptotically freeze and fade. From your own perspective, you continue inward. The universe does not always hand us one camera angle. So which is really true? In relativity, that question often needs more care than we expect. The outside observer never actually sees you cross in ordinary incoming light, because the signals become infinitely delayed and redshifted. But that does not mean your crossing does not happen in your own proper time. It does. These are not contradictory statements. They reflect the fact that space-time does not come with a universal master clock. Now let us talk about what might kill you first, because black holes are scientifically elegant but personally unfriendly. The famous term here is spaghettification, and unlike many dramatic-sounding science words, this one is memorable because it is almost cartoonishly vivid and also essentially accurate. Spaghettification happens because gravity weakens with distance, and near a compact object like a black hole, that change can be very steep over short distances. If your feet are closer to the black hole than your head, gravity pulls more strongly on your feet than on your head. At the same time, the sides of your body are squeezed inward. The result is stretching along the direction toward the black hole and compression across it. You become long and thin, at least in the equations. It is one of the worst possible fitness plans. These are tidal forces. We experience a mild version from the moon and the sun raising tides on Earth's oceans. The side of Earth facing the moon feels a slightly stronger pull than the far side. On a black hole, that difference can become murderous. But here is another surprise. Whether you are torn apart before reaching the event horizon depends on the black hole's mass. For a relatively small stellar mass black hole, perhaps a few times the mass of the Sun, the event horizon is also relatively small. The gravitational gradient near it is steep. Tidal forces become extreme well before or around the horizon, and you would be pulled apart long before any quiet crossing. In that case, falling into the black hole would be violently fatal outside the event horizon itself. For a supermassive black hole, however, the horizon is much larger. Although the total gravity is immense, the change in gravity over the length of your body at the horizon can be much smaller. That means you could cross the event horizon of a sufficiently large black hole without being immediately torn apart. The black hole at the center of the Milky Way, Sagittarius a star, is about 4 million times the mass of the Sun. A black hole that large could let you pass the horizon before tidal forces became lethal. Your doom is delayed, not cancelled. This feels backward at first. Bigger black hole, gentler crossing. Smaller black hole, more brutal. But it makes sense once you focus not only on gravity itself, but on how quickly gravity changes with distance. A giant black hole spreads its horizon over a much larger region. It is still the end of escape. It is just not necessarily the end of your body at that exact line. So let us choose a supermassive black hole, because it gives the fullest version of the story. You are falling inward. Behind you, the outside universe remains visible, but it no longer looks normal. Light from the external universe is distorted, concentrated, and blue-shifted in some directions. Depending on your trajectory and the black hole's rotation, the sky can become brighter in strange places and darker in others. The black hole's gravity bends the entire surrounding view. Space no longer behaves like the quiet, empty stage we imagine. It acts like an optical engine, grinding the universe into warped patterns around you. The event horizon comes and goes, with no visible line, no ripple, no crack, no wall. This is one of the most unsettling parts of the entire idea. The crossing itself may be locally uneventful, even though it divides two absolutely different categories of existence. One where return is possible in principle, and one where it is not. If you tried to send a message outward after crossing, it would never escape. If you fired your engines outward, you could alter details of your fall, but not reverse it. Every future-directed path still leads deeper in. The horizon is not a place where danger begins. It is a place where the structure of possible futures changes. This makes black holes hard for the human mind to digest. We are used to danger announcing itself. A cliff has an edge. Fire burns. A storm howls. The event horizon can be silent. The universe has hidden one of its most final boundaries in pure geometry. Now the question becomes, what happens after the crossing? According to classical general relativity, if the black hole is non-rotating and uncharged, your journey ends at a singularity, a point where density becomes infinite and space-time curvature becomes infinite as well. That word, singularity, appears in almost every black hole discussion, and it is often treated as if it were a definite thing we fully understand. We do not. In physics, a singularity is often less a confirmed physical object than a sign that the theory we are using has run beyond its proper domain. General relativity predicts that collapse continues to this extreme endpoint. But general relativity does not include quantum mechanics, and near such extremes, quantum effects should matter. And so when we say singularity, what we really mean is that our current equations say something goes catastrophically wrong here. Still, if we follow the classical picture, your proper time from horizon to singularity is limited. For a stellar mass black hole, it might be tiny. For a supermassive one, it can be much longer, long enough that you would have time to think, observe, and understand the shape of your fate before tidal forces become overwhelming. And this is where the geometry becomes even more difficult and more fascinating. Inside the event horizon of a non-rotating black hole, the radial direction inward behaves somewhat like time. That does not mean space literally turns into time in a simple exchange, despite the way it is sometimes casually phrased. It means that moving toward smaller radius becomes as inevitable as moving toward later moments in ordinary life. You can no more choose to avoid the singularity than you can choose to arrive yesterday. Different paths remain possible. You can spin, you can fire thrusters, you can alter the details, but all future-directed paths terminate deeper in. Imagine floating on a river that approaches a waterfall. Far upstream, a strong swimmer can still reach shore. Closer in, the current becomes too strong. Past a certain point, all available motions, even the heroic ones, still carry you over the edge. That analogy is useful, though imperfect, the black hole is not pulling you through space like water dragging debris. It is shaping space-time so that escape routes stop existing. What about a rotating black hole? Because real black holes in the universe almost certainly spin, this matters. A rotating black hole is described by the Kerr solution rather than the simpler Schwarzschild solution for a non-rotating one. Rotation changes the structure significantly. Outside the event horizon, there is an additional region called the ergosphere, where space-time itself is dragged around by the rotating black hole. This effect is called frame dragging. In the ergosphere, space is so twisted by rotation that nothing can remain stationary relative to distant stars. Everything is compelled to move in the direction of the spin. Frame dragging is not just another strange side note. It means the black hole does not simply sit in space. It drags the local structure of space-time around with it. If a non-rotating black hole is like a deep gravitational pit, a rotating black hole is more like a pit with the surrounding geometry being stirred into a swirl. This leads to one of the most remarkable possible consequences. Energy can, in principle, be extracted from a rotating black hole, not from inside the event horizon, but from the ergosphere. Roger Penrose showed that under specific conditions, an object entering the ergosphere could split, with one part falling in and another escaping with more energy than the original object had. In practice, this is not how humans are likely to power future civilizations, but it reveals how subtle black holes are. Even near the ultimate trap, physics finds loopholes for energy exchange. For someone falling into a rotating black hole, the internal structure in the mathematical models becomes more complicated. Instead of a single, simple horizon structure, there can be inner and outer horizons, and the equations hint at exotic possibilities such as passage to other regions of space-time. But this is where caution becomes essential. These idealized solutions assume perfectly eternal, undisturbed black holes. Real black holes form from collapsing matter, interact with their environment, and are unlikely to preserve those elegant internal structures in the simple form the equations suggest. Tiny disturbances can become enormously amplified inside. What the mathematics allows in exact solutions is not necessarily what the universe permits in practice. So while wormholes and alternate universes make for irresistible storytelling, there is no good evidence that a real falling observer would travel through a black hole and emerge somewhere else. The responsible answer is less cinematic and more honest. The interior of realistic black holes remains deeply uncertain. There is another puzzle waiting here, and it is one of the biggest in modern physics. What happens to information? In quantum mechanics, information is not just gossip about particles. It is the detailed specification of a system's physical state. Quantum theory strongly suggests that information is not destroyed. If you know the exact quantum state of a system and how it evolves, the evolution is reversible in principle. But black holes seem to threaten this. If matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, where does the information go? Is it destroyed? Hidden? Encoded somehow in the radiation? Preserved on the event horizon? This is the black hole information paradox. To see why this is such a big deal, we need to talk about Stephen Hawking's famous insight. Black holes are not entirely black. At first, that sounds like a contradiction. If nothing can escape from inside the event horizon, how can a black hole radiate? The answer comes from quantum field theory in curved space-time. Empty space is not truly empty. It seethes with quantum fluctuations. In a simplified picture, pairs of particles and antiparticles can appear and disappear. Near the event horizon, the gravitational conditions can allow one member of such a pair to escape while the other falls in, making it appear that the black hole emits radiation. The real mathematics is more subtle than virtual particles being torn apart like a cosmic magic trick. But that image captures the rough idea. This radiation, called Hawking radiation, means black holes can slowly lose mass and eventually evaporate. For stellar mass and supermassive black holes, this process is fantastically slow, far longer than the current age of the universe by absurd margins. So if you fall into an astrophysical black hole, evaporation is not your immediate concern. But conceptually, it changes everything. Black holes are not eternal one-way dumpsters for reality. They have temperatures. They have entropy. They participate in thermodynamics. Entropy here deserves a moment, because it is one of the most astonishing links in physics. Entropy is often described as a measure of disorder, but more precisely, it is related to the number of microscopic arrangements consistent with a system's large-scale state. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional not to their volume, but to the area of their event horizons. That is bizarre and profound. It hints that the information content of a region of space may somehow be encoded on its boundary. This idea helped inspire the holographic principle, one of the deepest and most suggestive concepts in theoretical physics. If that sounds abstract, here is why it matters to the person falling in. The black hole is not just a place where matter disappears. It is a place where our theories of gravity, quantum mechanics, information, and thermodynamics collide. Falling into a black hole is not merely a dangerous trip. It is a descent toward the fault line between our best descriptions of the universe. Now let us return to the experience itself. Suppose you crossed the horizon of a supermassive black hole alive and intact. At first, you might not notice much in your body, but visually, the outside universe would become increasingly compressed into a bright patch overhead, depending on your trajectory. Light from the external cosmos could appear concentrated and distorted. The universe you came from shrinks into a warped, luminous region behind you in space-time, even if not simply behind in the ordinary visual sense. As you fall further, tidal forces grow. The difference in gravitational pull between your feet and your head increases. If you are falling feet first, the lower part of your body accelerates more strongly inward than the upper part. The stretching becomes real, then catastrophic. Long before any hypothetical singularity is reached in bodily comfort, ordinary matter gives up. Bones, organs, cells, molecules, atoms. The gradients become too large. The black hole does not merely crush. Depending on the direction, it stretches and compresses at once, pulling the structure of matter apart. Would you feel pain? In the human sense, probably for only a limited interval, if at all, before your nervous system itself is disrupted. There is no meaningful version of surviving this in any biological sense. A black hole is not a harsh environment that might be endured with better technology. Beyond some point, the very physical structure required for a living body ceases to remain intact. Yet even here, black holes resist a simple image. People often imagine falling into one as being crushed into a tiny ball immediately. But near the horizon of a supermassive black hole, the first lethal effect would more likely be tidal stretching later on, not instant flattening at the boundary. And even later on is relative. It may still happen quickly on human scales. The exact timeline depends on the black hole's mass and spin and on your trajectory. There is another weird consequence of falling in. Communication and causality begin to separate your story from the outside universe's story. Events outside can still in principle affect you after you cross, because light or matter that also crosses later can catch up under certain conditions before deeper regions intervene. But your ability to influence the outside is gone. The asymmetry is absolute. This one-way character is why event horizons matter so much. Physics often respects symmetry. Black holes build in a hard directional break. And then there is the question many people quietly carry beneath all of this. Would you know with certainty that you had crossed? If the black hole is large and the crossing region smooth, perhaps not from purely local measurements in that instant. Locally, free fall feels weightless. Einstein's equivalence principle tells us that in a small enough region of space-time, being in free fall can feel like drifting in gravity-free space. You need information about the wider geometry to know what has happened. The horizon is a global feature of space-time, not a local wall with a sign on it. And that is why you could cross it without a sharp physical cue. This can be hard to accept because we expect reality's important boundaries to be physically marked. But many deep features of physics are not local in the simple way our senses prefer. The event horizon is defined by which paths can ultimately reach distant observers. That is a statement about the overall causal structure, not something your skin can necessarily detect at one precise instant. Now we come to one of the most disputed and thought-provoking ideas in modern black hole physics, the firewall paradox. In the traditional view, crossing the event horizon of a sufficiently large black hole should be uneventful, in accordance with general relativity. But when physicists tried to reconcile this with quantum mechanics and the preservation of information, and some argued that the horizon might not be smooth after all. Instead, quantum effects could create a kind of energetic barrier, a firewall, that would destroy an infalling observer at the horizon. This proposal arose from attempts to resolve contradictions involving entanglement and information flow in evaporating black holes. Do firewalls exist? We do not know. The idea is important because it shows how incomplete our understanding still is. General relativity says one thing. Certain quantum arguments seem to pressure that picture. Various resolutions have been proposed. Maybe there is no firewall. Maybe the interior is encoded in surprising ways through holography. Maybe space-time itself emerges from quantum entanglement, so that the apparent contradiction dissolves in a deeper theory. At the moment, there is no experimental test that settles the matter for astrophysical black holes. So the honest answer is that the smooth crossing picture is what classical relativity predicts. But quantum gravity may alter the story. Quantum gravity. That phrase sits in the background of almost everything about black holes. It is the missing framework, the theory we do not yet fully have. We have general relativity, which describes gravity and space-time with extraordinary success on large scales. We have quantum mechanics, which describes matter and forces with extraordinary success on small scales. But in places where both should matter intensely, such as the earliest moments of the universe and the cores of black holes, the two frameworks resist full reconciliation. Black holes are not just astronomical objects. They are laboratories for the unfinished business of physics. Sometimes people ask whether black holes are portals. It is an understandable question, because the mathematics of relativity contains tunnel-like solutions known as wormholes. In principle, certain equations allow bridges between distant regions of space-time. But stable, traversable wormholes would seem to require exotic conditions, such as negative energy densities of a kind not known to exist in the needed form on useful scales. And even if wormhole-like structures arise mathematically in black hole solutions, there is no good evidence that a real infalling traveler would use them as a shortcut. Reality, once again, seems less accommodating than fiction. What about being ripped apart, not by tides, but by radiation outside the black hole? This is an important practical point. And real black holes that are actively feeding can be surrounded by accretion disks so hot and violent that you would be dead long before crossing the horizon. Jets launched from the vicinity of some black holes blast matter and radiation across intergalactic distances. Magnetic fields, shock waves, and high-energy particles make the surroundings lethal. So when we imagine a clean plunge through the horizon, we are usually assuming an idealized black hole in an otherwise quiet environment. The interior story is difficult enough. The exterior neighborhood may already be unsurvivable. Now let us slow down and really picture the approach in stages, because this is where understanding often clicks. Far away, the black hole is a gravitational object like any other, though perhaps unusually massive and dark. You can orbit it, you can pass by it, and so, if you stay at a safe distance, it is just part of the architecture of the cosmos. Closer in, lensing begins to reveal that ordinary geometry has been compromised. The sky distorts, light bends. A dark center forms not because the black hole is a visible object, but because there is a region from which light does not reach you. Closer still, orbital motion changes. There is an innermost stable circular orbit. Outside it, matter can circle stably. Inside it, stable orbits no longer exist, and matter tends to spiral inward. This matters in accretion disks and in understanding how black holes feed. There comes a point where nature has run out of stable ways to remain nearby. The black hole does not have to drag matter in by force. It simply removes the possibility of staying put. Then comes the event horizon, for which the mathematical border of no return. And after that, if classical relativity remains valid, the infall toward the singularity. This stepwise picture is important because it shows that falling into a black hole is not one event, but a layered process. There is the dangerous environment around it. There is the optical weirdness of strong gravity. There is the horizon, which matters profoundly, but may feel locally uneventful. There are the tidal forces, which may kill you before or after the horizon, depending on the black hole. And there is the deep interior, where physics approaches territory we do not yet know how to describe with confidence. There is also a very human temptation to ask for the exact image, the final photograph, the precise interior movie. Science can take us far, but not all the way. We can say with confidence that black holes exist. We can say with confidence that event horizons are real features in our best models and strongly supported by observations. We can say with confidence that tidal forces near many black holes would destroy a person. We can say with confidence that time is distorted by strong gravity, and that outside and inside observers describe the approach differently. But when it comes to the ultimate fate of information and the exact nature of the singularity or the deep interior, confidence drops. That edge of ignorance is not failure. It is where the frontier actually is. There is something else black holes reveal, and it is easy to miss because the subject feels so exotic. A black hole is not a violation of the laws of physics. It is, in a sense, the laws of physics being followed with such uncompromising seriousness that the result becomes almost impossible for us to intuit. General relativity says mass and energy curve space-time. Black holes are what happens when that curvature goes extreme. Quantum theory says empty space is not empty, and information matters. Black holes force those claims into confrontation. The weirdness is not evidence that nature has become irrational. It is evidence that our intuitions were built for grasslands, weather, and falling rocks, not for collapsed stars and warped time. Let us look more closely at the outside observer's view, because it is one of the most misunderstood parts. Imagine your friend watching from a safe distance with a clock and a telescope. As you approach the horizon, your signals are increasingly delayed. Each pulse of light takes longer to climb out of the deep gravitational well. Each pulse also loses energy and shifts to longer wavelengths. Your image reddens, dims, and slows. Eventually, in practical terms, you fade from view. To the distant observer, you never quite cross. It is tempting to turn this into a paradox and ask, then how can the black hole ever grow if nothing is seen entering it? The answer is that the outside description still allows the black hole's mass and gravitational field to reflect incoming matter effectively. The horizon itself can be understood in ways that account for this, without requiring the distant observer to literally watch every final instant in real time. What matters observationally is that infalling matter becomes causally inaccessible, and its external influence gets absorbed into the black hole's evolving properties. This brings us to another important fact. In the simplest classical picture, black holes are astonishingly simple externally. According to the no-hair theorem idea, once a black hole settles down, it can be described by just a few properties: mass, charge, and angular momentum. Everything else about what formed it or fell into it is not visible in detailed form from outside. A black hole formed from a star, and one formed from an absurdly large archive of handwritten recipes would, if their mass, charge, and spin matched, look essentially the same from the outside, and nature can be brutal in its compression of detail. That simplification is one reason the information paradox bites so hard. If all the rich detail of what falls in gets reduced to a few external numbers, how does the universe preserve the deeper quantum information it is supposed to preserve? Black holes take a seemingly detailed history and turn it into a stark exterior summary. That is elegant, terrifying, and conceptually explosive. Now imagine, for a moment, a practical mission. Not a human one, because that would be ethically difficult to pitch to the review board, but a probe. A sophisticated instrument package approaches a supermassive black hole. It transmits data continuously. Images, clock rates, accelerations, particle flux, magnetic field measurements. From its own perspective, it sails through the horizon and continues sending until conditions become fatal to the hardware. From our perspective far away, the final outgoing signals become stretched, delayed, and feeble. We receive a long, fading whisper rather than a clean crossing report. In that asymmetry, the black hole becomes not only an object in space, but a limit on what can be known from outside. And yet we have learned astonishing amounts anyway. We have seen stars orbit the supermassive black hole at our galaxy's center, tracing invisible mass with beautiful precision. We have detected gravitational waves from merging black holes, confirming their existence through the ringing of space-time itself. We have even produced horizon-scale images of black holes through networks of radio telescopes spread across Earth, effectively creating a planet-sized observatory. The dark shadow in those images is not the event horizon itself, but the lensed silhouette created by the black hole's effect on surrounding light. Even that distinction matters. Black holes train us to be precise. There is a tendency in popular imagination to treat black holes as endings, and in one sense, they are. Cross the horizon, and escape ends. Fall deep enough, and life ends. Reach the classical singularity, and the equations end. But black holes are also beginnings. They began new fields of study in thermodynamics, quantum gravity, information theory, and observational astronomy. They turned Einstein's equations from abstract geometry into some of the most dramatic predictions ever tested. They forced physicists to confront the incompleteness of our deepest frameworks. They opened doors by closing paths. Sometimes people ask what it would look like if Earth fell into a black hole. The answer depends entirely on the black hole's mass and environment. A stellar mass black hole passing close enough to capture Earth would subject the planet to catastrophic tidal forces long before any horizon crossing. The planet would be torn apart into streams of debris. A supermassive black hole could allow Earth to remain intact longer as it crossed, but the overall orbital dynamics and radiation environment would still make the story apocalyptic. Oceans would slosh under tidal stresses. The crust would strain. The sky would warp. It would not be a subtle inconvenience. What if the black hole were tiny? Hypothetical tiny black holes, if they exist or could be created under extreme conditions, behave differently. A very small black hole has a tiny horizon and very strong tidal forces close in. It also radiates more intensely through Hawking radiation than a large black hole. But there is no evidence of dangerous miniature black holes wandering around swallowing planets. This is one of those ideas that gets more attention in fiction and headlines than in the actual astrophysical hazard list. We should also say something about charge. In many textbook black hole solutions, charge appears as one of the defining external properties. But astrophysical black holes are expected to be nearly electrically neutral overall, because any significant charge would attract opposite charge from surrounding plasma and quickly neutralize. So when we imagine a real black hole in space, mass and spin matter far more than net charge. If all of this still feels slippery or monhana, that is normal. Black holes force together three things the brain does not naturally like: extreme scale, counterintuitive geometry, and observer-dependent descriptions. We like the world to have fixed backgrounds and shared clocks. Black holes take both away. They remind us that space is not a stage, and time is not a universal metronome. They are dynamic, stretchable parts of the physical world. There is a beautiful and unsettling phrase sometimes used in relativity: light cones. At every event in space-time, the possible future paths of light define a cone-like structure, and the possible future paths of matter must lie inside it. Near a black hole, these light cones tip inward. Outside the horizon, some future light paths still point outward enough to escape. At the horizon, the outward path of light skims the boundary. Inside, even light's future points inward. This is one of the cleanest ways to understand the event horizon. It is where the structure of future-directed possibility closes. That image is abstract, but it can be felt. Imagine standing in a landscape where every road slowly begins to slope toward the same abyss. At first, you can still leave. Then the paths narrow. Then the final ridge is crossed, and every remaining route descends. The black hole is not merely a strong destination. It is a remapping of what destinations are possible. Let us now consider one more subtle point. Does an infalling observer see the entire future of the universe before crossing? This is a common claim, and it is often overstated. Because of gravitational and relativistic effects, the infaller can, in some scenarios, receive light from external events that occur later than events synchronized in ordinary distant coordinates. The outside universe may appear sped up in certain directions, but this does not mean you literally watch the infinite future of the universe play out like fast-forwarded film before you cross. In realistic conditions, what can be seen is limited by geometry, by available light, by the black hole's properties, and by the finite proper time of the fall. Some versions of this idea become distorted in retellings. The real answer is subtler and less theatrical. Another subtlety: from your own perspective, are you always in free fall and weightless? Only if you are actually falling freely. If your spacecraft fires engines to hover near a black hole instead of falling, smankano, you would feel enormous acceleration. Hovering close to the horizon of a black hole requires absurd thrust, diverging toward impossibility as you approach the horizon. Free fall is, locally, the gentler state. Trying to resist the geometry can be far more physically punishing than yielding to it. That matters because black holes challenge one of our default intuitions about danger. We tend to think active resistance means safety. Near a black hole, burning fuel to stay still can be the harsher experience. Free fall, paradoxically, can feel calmer right until it does not. Now, if we zoom out from the falling person to the broader universe, black holes are not rare curiosities. Stellar mass black holes should be abundant throughout galaxies, the remnants of massive stars. Supermassive black holes appear to anchor most large galaxies. Some actively feed and blaze as quasars, outshining entire galaxies with the radiation from matter before it disappears. In the early universe, quasars were especially common, showing us that black holes have been major cosmic actors for billions of years. They help shape galaxy evolution through feedback, jets, and the heating of surrounding gas. So when we ask what happens if you fall into one, We are asking not just about an exotic death, but about one of the universe's central phenomena. Black holes also reveal something profound about collapse and concentration. A star is a huge thing. It shines. It has layers, turbulence, magnetic fields, and nuclear reactions. A black hole can emerge from a star, yet from outside it ends up described by a few clean parameters. Yet it is as if the universe can take one of its most complex macroscopic objects and boil it down to mass, spin, and near-neutral charge. Complexity falls inward. Simplicity remains visible. Whether that simplicity is fundamental or only apparent is one of the deepest open questions we have. If you want the starkest summary of what really happens when you fall into a black hole, it is this. First, the environment around many real black holes would probably kill you before the horizon did. If the surroundings were quiet and the black hole were supermassive, you could approach and cross the event horizon without noticing a sharp local boundary. A distant observer would see you slow, redden, and fade, never quite crossing in ordinary light. From your own perspective, you would continue inward in finite time. Once inside, escape would no longer be possible in principle, because the geometry of space-time would force all future paths deeper inward. Tidal forces would eventually grow strong enough to destroy your body. Beyond that, classical physics predicts an encounter with a singularity, while modern physics admits that our understanding there is incomplete and quantum gravity may change the final description. That is the answer. But somehow the answer feels bigger than the sequence itself. Because the true shock is not just that black holes kill. Many things kill. Stars explode. Radiation sterilizes. Vacuum freezes. The true shock is that black holes expose how strange reality becomes when gravity is allowed to fully govern the structure of space and time. They take ordinary concepts like inside, outside, before, after, seeing, falling, and escaping, and reveal that those concepts were always local habits, not universal truths. There is a reason black holes grip the imagination so powerfully. They are one of the few places where the universe feels almost philosophical without ever stopping being physical. They are not symbols. They are not metaphors. They are actual regions of the cosmos, where our basic mental furniture starts to wobble. They are where geometry becomes destiny. And they are deeply, almost painfully real. The stars orbiting Sagittarius. A star do not orbit a myth. The gravitational waves measured by LIGO and Virgo did not come from speculation. The glowing rings imaged by the Event Horizon Telescope are not artistic guesses. Black holes are out there, in ordinary astrophysical existence, doing what the equations and the observations together say they do. We can trace their influence across space and across time. We can infer their mergers. We can watch matter vanish toward them. We can model the warping of light around them. What we cannot yet do is follow the story all the way to the end with a complete theory in hand. That unfinished quality matters. It means black holes are not solved monsters in a cosmic bestiary. They are active frontiers. Somewhere in the attempt to understand what really happens inside, physicists may discover how space-time emerges, how information survives, or how gravity and quantum mechanics finally fit together. The fall into a black hole may be impossible to survive, but trying to understand it may help us survive our own ignorance. There is also something quietly humbling in the contrast between how invisible the horizon is and how final it is. We tend to imagine the universe marking its deepest boundaries with noise and spectacle. Sometimes it does. Supernovae announce themselves. Collisions flare. Jets roar across galaxies. But the event horizon can arrive in silence. That is a lesson beyond black holes. Nature does not owe significance a dramatic surface. Some of the most absolute transitions in reality happen without a visible line. And then there is the emotional side of this, which is easy to dismiss and hard to avoid. To picture yourself falling toward a black hole is to confront both fear and fascination. Fear because it is annihilation on terms the body cannot negotiate. Fascination because it is annihilation wrapped in revelation. The black hole does not merely end the traveler. It shows, almost cruelly, how much richer the universe is than the everyday world suggests. Space can bend. Time can split into differing accounts. Light can orbit. Futures can close. Entire stars can become a darkness with temperature and entropy. And at the core of it all, our best theories can still reach a point where they simply say, beyond this, we do not know. That is not a weakness in the story. It is the reason the story remains alive. Black holes remind us that knowledge is not a collection of finished answers. It is a map with beautifully drawn regions and dangerous blank spaces. And sometimes the blank spaces begin exactly where the known laws become most extraordinary. We are a species that evolved under a small star on a rocky world. And yet we have learned enough to predict event horizons, measure relativistic time shifts, detect black hole mergers from billions of light years away, and seriously debate the fate of information in evaporating space-time. That is an astonishing thing for matter arranged into human brains to be doing. So what really happens when you fall into a black hole? You enter a place where all roads inward become mandatory. To distant eyes, you slow and fade. To yourself, you cross in finite time. If the black hole is small, you are torn apart before or near the edge. If it is supermassive, the crossing may come first and the destruction later. The sky distorts, time loses its familiar simplicity, and eventually tidal forces erase the body, while the deeper interior passes from hard prediction into one of physics' greatest unknowns. And maybe that is the final wonder here. The black hole is not only an object that swallows matter, it swallows certainty. It is where observation gives way to inference, where intuition gives way to geometry, and where the universe quietly shows us that reality is not obliged to remain comfortable in the presence of truth. The next time you see an image of a black hole, a dark center ringed by fire, it is worth remembering what that image really represents. Not a hole in the sky, but a place where gravity has become architecture. Not a cosmic vacuum cleaner, but a region where escape ceases to exist. Not just an astronomical curiosity, but one of nature's clearest announcements that the universe is larger, stranger, and more severe than common sense ever prepared us for. And that may be why black holes continue to fascinate us so deeply. They are terrifying, yes, but they are also clarifying. They strip away the illusion that reality must be intuitive to be real. They show us a cosmos that is lawful but not tame, comprehensible in part, and still mysterious in depth. They remind us that wonder is not the opposite of understanding. Often, it is what remains after understanding has done its best work. So if you ever fell into a black hole, There would be no dramatic splash, no visible edge, no return. There would be warped starlight, diverging clocks, one-way futures, and at the end of the known story, a region where our equations run out before the universe does. That is what makes black holes so unsettling and so beautiful. Thank you for watching, and I will see you in the next one.